So the number of days it takes to complete a project is inversely proportional to the number of workers hired for the project. So days inversely proportional to workers. So we would say days, we'll just say days, is inversely proportional to workers. K is my constant. All right, so then I just fill in what I know. How many days did they give me? 54. That should equal some constant over how many workers? 4. To find K, I multiply both sides by 4, so K is going to equal this little guy right here. Now I know that days equals 216 divided by the number of workers. Now they want me to answer this question. How many days are needed to complete the project with 18 workers? Just going to fill it in. How many days is it going to take for 18 workers? 216 divided by 18. But these parent functions are the ones that you want to know. You should recognize that when you see an absolute value, it's going to be a v, or when you see a quadratic in x squared, that it is going to be a parabola, okay? That should be your basics from prior knowledge that you can take with you when we start translating, which we did some translation last year. All right, so we are in page 46 in your books. Function operation. Nope. All right, so the first types of translations that or transformations that we have is translating. Translating just slides the function up or down, left or right. If you add or subtract outside of the parent function, it's going to go up and down in the way in which you think it would. A plus takes it up, a minus takes it down. If you add or subtract within the function, so like x squared plus 3, that's outside. X plus 3 quantity squared, that's inside. So that's the difference between those. They give you the example of the absolute value here. Absolute value plus 2, that is outside of the absolute value. It took the absolute value up 2. Absolute value minus 2, or minus 3 rather, it took it down 3, outside. For this one, they did the cubic function. This is the original cubic function. This is the parent function. If you look on your sheet of paper, x cubed looks like this. This is inside the function, and it moves opposite of how you think it would. A minus moves you right. A positive moves you left. It's inside the function. Okay? So they have x plus 3 quantity cubed inside the function. It moved it left 3. The function looks identical. It just slid to the left. X minus 2 quantity cubed, same function, but it slid to the right 2 units. These are vertical and horizontal translations. The next thing you can do with these is you can reflect. You can reflect it. So the parent function here is the square root of x, which is also one of your parent functions. You'll notice they have it right here. It's just this piece of it. It looks like half of a sideways parabola is what it looks like, okay? Square root of x, this is my parent function. When you have a negative on the outside of the function, it flips it over the x-axis. Think about reflections from like geometry and even last year when we did reflections. Negative is on the outside here. You'll notice it went from the parent function here. It flipped across the x-axis and now it's down here. All right? But when the negative is on the inside of the function, inside, it flips it across the y-axis. So here's my parent function. Inside, it took it across the y-axis. It's like a mirror image across the y-axis, all right? And so they have these reflections here. The first one they show us is a parabola. It's like a parabola. It's a little bit broader because it's to the fourth. I'm not going to make you know to the fourth, but they gave you the parent function. This is going to be a negative on the outside of that. So this guy is going to look like this. G of x is actually going to be a negative x to the fourth. The negative is going to be on the outside. All right. Here we have 1 over x. That's my parent function. It's a reciprocal function. It's on the bottom of your sheet. Here's my parent function, little dotted lines here. And for this one, it actually flipped across which one? Which one did this guy flip across? Yeah, it actually, so if you think about it, it actually flipped across the x-axis, is kind of, but it actually flipped across the origin. This guy flipped here, this guy flipped here. They gave us an origin one. You can take it and you can stretch it, or you can shrink it. All right? So if you look at this first one, they have a number on the outside. Let me shift these guys down a little bit so I can make this larger. All right, you'll notice that we went from our regular function and then we have this a. This is just a number on the outside. So my parent function is, again, that square root of x. That's this guy right here. They put an integer, a whole number here on the outside, a 2. And you'll see it stretched it. So it pulled it this way. A 2 on the outside pulled it this way, right here. All right. The 1/2, though, if we did this right here, the 1/2 on the outside, shrink it, all right? It shrank it this way. So this is a vertical stretch, a vertical shrink right here. All right, vertical stretch, vertical shrink. You'll notice when they put it on the inside over here, and this one they should have written incorrect. They wrote that incorrectly. That should have been on the inside. When they put the 1/2 on the inside, it actually pulled it this way. They look very similar, by the way. Stretches are hard to write unless you're doing like a absolute value or something like a linear. Those are easy because you actually have the slope, but that's actually what a slope is doing when you think about a line. So if I were to have, just really quickly, if I were to have a line and we have my standard line like this, that's my y equals x. What happens when you put a 2 in front of it is it stretches that this way, right? And if I were to put a 1/2 in front of it, it would actually pull it this way, right? And so linear is doing the same thing. A 2 in front is actually pulling it up. A 1/2 is actually pulling it down, right? And that's what's actually happening here. I will not make you do a lot of stretches and shrinks as far as this goes. I'm just going to make you recognize that something did happen in the front of it. So if I were to give you like a 2 squared of x, I would just want you to know that it's going to pull it up. I'm not going to say, oh, you didn't pull it up far enough or you didn't shrink it far enough. Does that make sense? So these are going to all be sketches. I'm going to be checking, do you know the parent function? Do you recognize that it's translating left, right, up, or down? And if there's a coefficient, do you know how it's affecting it? I'm not going to judge that you stretched it far enough or not far enough, as long as I can see that you indicated there was a stretch. Because these are hard to do without actually graphing it, without doing an actual graph. But one pulls it this way, the outside pulls it this way, and the inside pulls it this way, all right? Even though sometimes they look the same. So you'll notice that the 1/2 on the inside here looks very similar to this on the outside, but you can tell it's a little bit closer here versus just pulling it that way. It didn't come as far away from this when you put them on the inside, and this one's just written wrong, by the way. I'm not sure why they wrote it wrong, but you can see it didn't pull as far away as being on the outside. The outside pulled further away from the original function when it did that. All right, let's look at this example that I have down here. All right, so if you look at example 3, we have a parent function here of x squared. All right, so my parent function, we know that's my parabola. All right, a -3 would stretch it. Do you see how the -3, and ignore the negative right now, just the 3 is going to stretch it this way. All right, it's going to elongate that parabola, which is what happened with this red. And then the negative, this is why you don't have to worry. And about when you look up here, see how it's talking about absolute value? They don't care if it's positive, negative for the stretch piece of it. It stretched it the same. All the negative did was it reflected it down, okay? So the 3 is all you're looking for. Is it a whole number or is it a fraction? A whole number is going to pull it this way. A fraction is going to squish it this way, okay? Then you worry about if it's positive or negative. That just makes it reflect, okay? So it's not like a positive 3 stretches it one way and a negative 3 stretches it another. It does not. They stretch it the same. The positive keeps it in the correct orientation. The negative flips it, okay? So the positive 3, the absolute value of 3 stretched it like this, and then the negative piece of it flipped it down here. And so you can see where you started out at this black parent function, the 3 stretched it, and the negative piece of it flipped it. All right, look at this one. This is the same parent function. We have the same parent function here that would be here. They just didn't draw all of them, right? They didn't draw multiple ones because we didn't flip. Same exact parent function, but technically over 3, what is my coefficient there if it's over 3? 1/3. So you can see the 1/3 on the inside actually pulled it this way. All right, it actually pulled it this way. That's why outside and inside looks very similar, because it's just going to pull it further here when you have a fraction, because you've configured that it's being squared. Your fraction is being squared, whereas if it were on the outside, it's going to be a full 1/3, where technically it's like a 1/9 here because it's being squared. Does that make sense? And so you actually have a smaller fraction when it's on the inside. So it actually does the same movement, it just does it differently because it's being squared or cubed or whatever's happening on the inside. In that case, it was being taken the square root of, so it's actually the square root of 1/2 is actually going to be a bigger fraction than the square of 1/2 would be a smaller fraction. So look at the top of page 35. Top of page 35. Multiple things can happen to one function. What you need to do first is say, what function am I talking about? So if I look at this first one, what is my parent function? If I look at this guy right here on my handout, what is my parent function for this first one? Which one is he? The quadratic, right? It is x squared. Okay, so I have two things happening to this x squared. I have a +3. The +3 is on the outside of the x squared. So that is what type of translation? Horizontal or vertical? Vertical. And it's doing exactly what it should do. So what it's actually taken is it's taken my vertex and it's moved it up 3. Up 3. My 2 is stretching it. So my parabola is normally like this. The 2 made it skinnier because it pulled it this way. If you were to take, have you ever had one of those little stretchy guys that are plastic? You pull it and you get skinnier, right? I mean, because there's less stuff. That's what's happening with this. That 2 is just stretching him this way, all right? And so you'll notice that it is actually skinnier than it would have been. So it moved up 3, it is skinnier, and then this negative in front of the 2 flipped it upside down, okay? So we have 3 things happening to this. We have a movement up and down, we have a stretching with the 2, and we have a flipping with the negative. All 3 things happen to this one. Look at the next one. This is also a quadratic, isn't it? Yes? Yes. The difference between this and the other one is my -2 and my 3 are on the inside. Okay? Now, when you have a negative on the inside of a quadratic, it is being squared. So technically it's supposed to flip over the y-axis, but it is a parabola that is symmetric to the y-axis. So you will not notice the flip because it looks the same when it flips across something it is symmetric to, okay? So the negative doesn't really affect it. The 3 and the 2 do. So you'll notice that we start out here. The +3 would actually move it negative, right? This is where your flip comes into place, right? So normally I would say this guy would move it here, and then it stretched it and flipped it. You're not going to notice the flip right here, but you're going to notice if it moves left and right and flips, right? So you're going to notice that it slid left 3, it reflected, and then it shrinks it actually because it's on the inside. But the horizontal and the vertical shrink look the same. So look at this guy here and look at this guy here. Even though the 2's on the outside, it affected it a little bit more because it squared it, right? So it's a little bit skinnier, but it's still a shrink. So it moved it over, then it shrunk it and reflected it, all right? And so reflection in the y-axis, horizontal shrink by 1/2. First thing I would do is I would actually rewrite this because I want it to look, in my head, I want to make sure I know what I'm actually looking at here. All right, so we have a lot of stuff going on. The first thing I need to establish is what exactly is my parent function. So when you look here, this is a cubic. How do I know it's a cubic? Well, I have that 3 on the outside of my parentheses. So my cubic function, if I were to sketch it, and I'm just going to sketch it in like a highlight color so that you can see it. All right, he's going to look similar to this, right? So I have just that guy going on. That's my parent function, all right? Once I know my parent function, I am going to decide, am I moving left or right and up and down? Okay, left, right, up, down. And so when you see it this way, I have a movement on the inside and on the outside, don't I? I have a movement on the inside and on the outside. What's my inside movement? It's a 2, right? So is that left or right? Left, okay. And so naturally this guy is going to move here, all right? And so we have this movement right here, okay? I also have an up and down movement. I have an outside. So this 2 right here moved me left. What is this 4 going to do? It's going to go down. And so I'm down here with this 4, okay? And so I have this, I'm just going to dash it. I have this thing going on right here. All right? I also have a reflection happening, don't I? Is my reflection on the inside or the outside? So which axis am I going to reflect over? Inside is my Y, right? And so if I were to take this and reflect him across the Y, he's going to be over here. So I would take this vertex and I would say I'm 2 away from my Y, right? So I should be 2 away over here, but I'm reflecting. Think about mirror image. So I started going from down to up. If I were to put a mirror here, it's actually going to do it the opposite way. It's actually going to do this. Does everybody see that? So if I were to take this guy and reflect it, he's going to reflect like that. It's truly a mirror image, right? I have one more thing going on. So I have accounted for my movement, left 2, down 4. I have accounted for my reflection. What have I not accounted for? This 1/2. Does the 1/2 squish it or stretch it? It squishes it, doesn't it? Right? And so he's actually going to get a little bit fatter than this. So he's still going to be reflected, but he's actually going to be this chunkier, so to speak, little guy. I'm going to do him in a different color. He's actually going to be a little bit wider. Okay? So my original parent function is smaller. A 1/3, I think is what it was. Yeah, 1/3 in front is going to do this to it. And so imagine taking that line and squishing it. It's going to spread it out. Think of like Play-Doh, okay? If you squish Play-Doh, it goes out this way. If you pull it, it gets skinnier, okay? A 1/3 is going to squish it, so it's going to get fatter in your drawing. So when you have reflections, move it first, then reflect, then do your shrink or your stretch, okay? Do your translation movement, your reflection, then your stretch or shrink. Question. right? So for homework, I only want you to do the first page right here. 22 and 25 from this first page. Graph it and write the rule, which we didn't really talk about writing the rule, but you should be able to from the graphing. So graph this guy, write the rule for that guy. By rule, it just means write the function. Oh, okay. So for 22, they've given you the function. They want you to graph it. For 25, they've given you the graph. They want you to write the function. So you only have to do these two.